Hello friends, welcome to my channel. This is Isro question paper from 2006 to 16 strength of material. Question is, a frame of two arms of equal length L is shown in the figure. The flexural rigidity of the arm frame is EI. The vertical deflection at the point of application of load P is how much? Here vertical deflection, how much? It will deflect like this. Here he asked vertical deflection how much. So here in two parts we will do. First one, we mark it as A, B, C. BC first take. Here point load P. It will deflect like this. For first one, let delta 1 is the deflection, length is L for point load P. And for second one, here A and B. The eccentric load P, it will act like one moment M equal to P into L, and one axial load here P. If you resolve P, it will act like this. And this is point B, C. This is A and B. Here it will deflect like this. Theta, here L. Delta 2. So total deflection at the point of application of load P will be delta 1 plus delta 2. Here I will do this one. For first part, cantilever beam with point load. Delta 1 we know already discussed. Delta 1 equal to PLQ by 3 EI. And for second one, P. Slope. Slope will be, for moment we know already, ML by EI. So M is PL into L by EI. So it's PL square by EI. So deflection delta 2 will be theta into L. So PL square by EI into L, it PLQ by EI, it is I. So total deflection at the application of point load P will be delta 1 plus delta 2. It's PLQ by 3EI plus PLQ by EI. Plus 3 PLQ, so it will be 4/3 PLQ by EI. From option 4/3 PLQ by EI. C is the answer. This is very important for GATE examination. Already asked in GATE examination this same question. A thin cylindrical cell of diameter D, length L and thickness T is subjected to an internal pressure P. The ratio of longitudinal strain to hoof strain is how much? Thin cylindrical cell. So hoof stress is greater than longitudinal stress. Here principal stress or hoof stress is PD by 2T. Sigma 2 is longitudinal stress PD by 4T. So the ratio of longitudinal strain to hoof strain. First we will take sigma. Here one more thing is I am taking mu here given as 1 by m. M given. So mu equal to 1 by m. Poisson's ratio is 1 by m. In this question not mentioned. You have to assume it. So longitudinal strain to hoof strain. Longitudinal strain is sigma 2 by E minus mu into sigma 1. So sigma 2 is PD by 4T E minus mu into PD by 2T. PD by 2T. Here E. 2T take common. 1 by 2 minus mu is equal to PD by 4TE 1 minus 2 mu, and our sigma 1 strain due to hoof stress by E minus mu into 2 by E. Here sigma 1 PD by 2TE minus mu into PD by 4TE. Take common PD by 2TE 1 minus mu by 2. So PD by 4TE so 2 minus mu. So sigma 2 by sigma 1 is PD by 4TE minus into 1 minus 2 mu divided by PD by 4TE into 2 minus mu. Mu is 1 by m. So if you put mu as 1 by m, finally you will get m minus 2 by 2m minus 1. So it's a the answer. Or again I am doing sigma 2 by sigma 1. Strain due to longitudinal stress and strain due to hoof stress. PD by 4TE 1 minus 2 mu divided by 4TE 2 minus mu. Cancel. Take mu as 1 by m. So 2 into 1 by m by 2 minus 1 by m. M minus 2 by m, 2m minus 1 by m. M cancel. We'll get m minus 2 by 2m minus 1. A vertical column has two moments of inertia, Ixs and Iy. The column will tend to buckle in the direction of dash. Column, we know already from Euler's pi square Ei by, this is I minimum. This one they asked in this question. I minimum tend to buckle in the direction of minimum moment of inertia. D is the answer. For the component loaded with a force F as shown in figure, the axial stress at the corner point P is how much? In this point they asked how much axial stress. So here what we will do, this force F will resolve as, here we will take like this, one force F and one force F. They will balance each other. So this force and this force F, they will provide one couple. Couple with moment F into L minus B, and one more, this tensile force F, axial force tensile in nature F. So finally what we will get here, we will get one moment like this, clockwise moment F into L minus B, and one axial force F. They asked in this point P point how much axial stress. So that section also next page I will do. Here it's like this. This is F, and section is like this, 2B and cross section 2B and 2B. Here this is L. So here axial stress sigma A equal to F by area, F divided by 2B into 2B, cross sectional area. So we'll get F by 4B square. From bending moment, bending stress is M into Y maximum by I. So M already we got, F into L minus B to Y maximum is 2B by 2, it's B So I is B dq by 12. 2b into 2bq by 12. If you solve this one, b cancel, 2 16, here 2q is 8, 2 12 is 6, this is 8, okay, 3 by 4. So finally we'll get f into L minus b divided by bq. So here this side tensile, this side compressive. Sigma b bending stress plus axial stress. This side is minus sigma b plus, because it is in compressive nature and axial stress is tensile, so it is positive. These things already discussed in my previous video. The point is, our point P is here. So here we have to get the stress value. So this side at extreme point, sigma bending stress plus axial stress, 3 by 4 F into L minus B by BQ plus axial stress for B square. Both sides 4BQ 3F into L minus B plus 1B, you have to multiply here F by 4BQ, take outside, and 3 L minus B plus B. To solve this one, F by 4BQ into 3L minus 3B plus B. Finally we will get F by 4BQ into 3L minus 2B. This is stress at P point. So from option, F by 4BQ into 3L minus 2B. F by 4BQ into 3L minus 2B. D is the answer. A massless beam has a loading pattern as shown in the figure. The beam is of rectangular cross section with a width of 30 mm and height of 100 mm. The maximum magnitude of bending stress in megapascal is given by how much? It will be like this. Simply supported beam UDL A, B, C. Here RA, RC. This is 3000 Newton per meter. These are 2000 mm. Here BC 2000 mm. We have to find the maximum magnitude of bending stress, cross section given. Cross section. So it's B and H. H is 100 mm, B equal to 30 mm. Omega value you convert in its Newton per mm, Newton per meter, you convert it divided by 1000 Newton per mm. So it's 3 Newton per mm UDL. So RA plus RC here UDL. See, RA plus RC equal to 3 into 2000 BC distance. So this is sigma x equal to 0. Summation of forces along x direction. Then taking moment about C point, RA into 4000 mm equal to 3 into 2000 into 1000. So RA will get 3000 by 2 is 1500 Newton. So RC equal to total RA plus RC equal to this much. So RC equal to 6000 minus 1500. It will come 4500. Then take B to C, shear force at x distance. We know where shear force will 0, their bending moment will be maximum. So B to C you take shear force minus RC plus 3 into x. Let it be x, this distance. So for shear force 0, RC equal to 3 into x. RC we got 4500 divided by 3 equal to x. So we got the distance. This x is 1500 mm, where the bending moment is maximum. So that x point bending moment how much we'll get? We'll calculate RC into x minus 3 into x by 2. So it will come M maximum 3 into 1500 into 1500 minus 3 into 00 by 2 will get 3 into 00 into 750. So we know bending stress is M by I into Y maximum. Put the value 3 into 1500 into 750 divided by I is BHQ by 12, 30 into 100 into 100 into 100 by 12. Then here Y maximum is 100 by 2. So 100 cancel. Then here 2 0 cancel, single zero cancel, 3 cancel. Finally 25 into 3, 25 into 4, 4 into 3 12. Then 45 into 3 by 2 will get 67.5 Newton per mm square. From option B is the answer. Next, PLQ by 3A is the deflection under the load P of a cantilever beam, length L, modulus of elasticity E, moment of inertia I. The strain energy due to bending is how much? Deflection under load, strain energy already discussed. Delta is PLQ by 3A. Strain energy half P into delta. So half PLQ by 3EI into P. Finally you will get P square LQ by 6 EI. B is the answer. Two steel rails, each of 12 meter length, are laid with a gap of 1.5 mm at ends at a temperature of 24 degrees Celsius. The thermal stress produced at a temperature of 40 degrees Celsius is E given Young's modulus, and your coefficient of thermal expansion alpha given. So two rails, L is 12 meter, gap is 1.5 mm. Initial temperature T1 is 24 degrees Celsius. Final temperature T2 is 40 degrees Celsius. So delta T is T2 minus T1, it's 40 minus 24, 16 degrees Celsius. Young's modulus 2 into 10 to the power 5 Newton per mm square, and alpha coefficient of thermal expansion, it's 12 into 10 to the power minus 6 per degree centigrade. Here we will get two stresses, thermal stress and axial stress, or our normal stress. This is the gap. If gap is not available, it will expand like this. So two stresses we will get. First we will check for axial stress. We know stress by strain is E, and our delta L is PL by AE. So del L, This distance is 1.5 mm already given. 0.5 equal to P by A is sigma stress 12 into 10 to the power 3 12 meter length divided by 2 into 10 to the power 5. So sigma finally we will get 100 into 1.5 6 1.5 is 10 here 15 10 3 5. So we'll get 3 into 15 is 5 25 Newton per mm square. This is axial stress produced due to that gap. And our thermal stress alpha Te, I'll change the color, alpha Te. So alpha 10 to the power 6 into T already we got 16 delta T change in temperature E 2 into 10 to the power 5. So it's 10 then 2 5 12 into 16 by 5. So 12 into 16 2 7 12 into 1 12 plus 7 it's 92 192 by 5. So we'll get 3 then 8.4 38.4 Newton per mm square. So actual thermal stress, this is without this barrier. If it will expand from this to this, if gap is not there, no, then this thermal stress you will get. Gap is there, so you have to let it be sigma T dash minus that axial stress due to that gap 38.4 minus 25. So we get 13.4 Newton per mm square per megapascal. From here see the answer. An aluminum tensile stress specimen has a diameter D0 equal to 25 mm and gauge length of LO equal to 250 mm. If a force of 175 kN elongates the gauge length by 1.25 mm, the modulus of elasticity of the material is nearly how much? Modulus of elasticity. Here data given DO is 25 mm, original length LO it's 25 mm, P equal to 175 into 10 to the power 3 Newton. Change in length 1.25 mm. So stress by strain equal to E stress equal to P by A load by area of cross section. Stress equal to P by A. P how much? 175 into 10 to the power 3 divided by area of cross section pi by 4 into 25 into 25, 625, 25 into 25 square. It's 7, then 25 into 40,000. So you will get 7 into 40 into 4 by pi. Strain is del L by original. Change in length to original length. 1.25 by 25. So this is 125 by 100. Cancel this one. 1.5 by, here LO is 250, this one 250 mm, so here you put 250, 25 into A, this one 10, so 100, 5 by 10 is 2, we'll get 1 by 200. So finally E, you will get 7 into 40 into 4 is 160 by pi divided by strain how much? 1 by 200. By 200 means it will multiply. 7 into 160 into 200 by pi. If we calculate this one, 10 by pi, you take approximately 3. So if you calculate this one, we will get 67.2 Newton per mm square or megapascal. Here it's nearly megapascal. 67.2 into 10 to the power 3 Newton per mm square or megapascal. So it's nearly 67.2 gigapascal. So this one not possible, this one not possible. Approximately 71 gigapascal. So A is the answer. Next question. A cantilever beam of length L is subjected to a concentrated load P at a distance of L by 3 from the free end. The deflection at the free end how much? So cantilever beam subjected to a point load P at a distance of L by 3. So it's like this. This person is curve and this person is straight line because no load. Here theta is the slope. Here also same slope theta. So there is deflection here. Total deflection delta. Delta 1, delta 1. Here delta 2. This force is P. Here L by 3. Total length is L. So delta 1 will get L by 3 from this area. This is 2L by 3 delta 1 PLQ by 3I. So already discussed this one. 3 by EI. 8LQ by 3Q is 27 into 3 EI. Then our slope theta 1 or theta PL square by 2EI. P into 2L by 3 square by 2EI. Get 4PL square by 9 into 2EI. And deflection delta 2 is multiply slope is slope multiplied with L by 3. So if we multiply, we will get L by 3 into 4PL square by 9 into 2EI. We'll get 2PLQ by 27EI. So finally delta equal to delta 1 plus delta 2. Delta is 8PLQ by 81EI. 3 into 27 plus 2PLQ by 27EI. If we solve this, we'll get 14 by 81 PLQ by EI. B is the option. This is very, very important for GATE also. Next question. Match the item column 1 and column 2 matching. A. Resilience. All are important for all exams. Resilience, fatigue, stiffness, elasticity. A. Ability of material to return to the original shape when load is removed. This is elasticity. Capacity of material to absorb energy elastically. This is resilience. Ability of material to absorb certain amount of energy without failure. This is stiffness. When load is removed. Resistance of material to elastic deformation. Failure of material at loads less than at normal condition. 5 is fatigue. So we'll do A, B, C, D. Resilience is capacity of material to absorb elastical. 2. B, fatigue. Fatigue is failure of material at loads less than at a normal condition. B is 5. So A, 2, B, 5. C is not possible. B also not possible. Then you go for stiffness and D, elasticity. Stiffness is resistance of material to elastic deformation. This is resistance of material to elastic deformation. Capacity of material to absorb energy is, this is your strain energy, resilience, these things it will come. C is 4 and D Elasticity, ability of metal to return to the original shape when load is removed. D is 1. From option, it's D. Thank you friends for watching my video. If you like my video, then subscribe it. Thank you. This is the end of strength of material question paper, Isro question paper. Thank you.